Post-war British planners reviewed infantry small arms requirements. They studied German assault rifles and Soviet carbines. Reports described automatic fire with controllable recoil. Committees noted rifle cartridges were heavy and inefficient. Infantry sections carried ammunition loads limiting sustained fire. War Office memoranda requested an intermediate power cartridge. The ideal cartridge panel began formal calculations. Spreadsheets showed trade-offs between recoil, range, and penetration. Recommended bullet diameters clustered around 7 mm. Draft minutes outlined velocity and energy envelopes. Designers at Enfield received these numeric constraints. They were tasked to translate tables into hardware. The result became the .280 British cartridge. It used a rimless bottlenecked case geometry. An overall length remained shorter than .303 service ammunition. Pressure limits were set below full rifle levels. The cartridge aimed for flat trajectory to typical engagement distances. Trial notes emphasized controllable automatic fire from shoulder. While ammunition development continued, rifle concepts proliferated. One line produced conventional stocked prototypes. Another line considered a compact bullpup arrangement. The bullpup placed the action behind the trigger. Overall length shrank while preserving barrel length. This configuration offered improved handling in confined spaces. Engineer Stefan Janssen led the bullpup program. His design group worked inside RSAF Enfield. Drawing offices produced first layout prints for EM2. Blueprints fixed receiver dimensions around the .280 cartridge envelope. Bore axes, sight lines, and magazine position were harmonized. Tolerances were typed in narrow columns along margins. The EM2 used gas operation with flapper locking. Gas tapped from the barrel drove a piston. The piston conveyed movement to the bolt carrier. Radial flaps engaged recesses in the receiver walls. Unlocking occurred after bullet exit and pressure drop. This sequence kept locking stresses within acceptable limits. Receivers were machined from forged steel blanks. Milling machines removed excess metal in sequential passes. Fixtures clamped receivers along reference datum surfaces. Operators checked dimensions with plug gauges between passes. Inspection sheets recorded each rejected receiver by serial. Surface finish requirements specified uniform machining marks. The barrel remained relatively long for an assault rifle. The length figures matched required ballistic performance with .280. Longer barrels improved velocity and retained energy down range. Rifling twist optimized stability for the chosen bullet weight. Chamber dimensions followed ammunition committee drawings closely. Proof testing occurred with the overpressure rounds from Radway Green. The bullpup architecture moved the magazine rearwards. Magazine wells sat behind the pistol grip. Feed angle aligned cartridges smoothly with chamber axis. Designers aimed to reduce feedway friction and stoppages. Magazine capacity matched contemporary expectations for automatic rifles. Sheet steel bodies were spot welded and heat treated. Controls reflected British training habits and ergonomics. Combined fire selector and safety lever was adopted. The lever provided distinct tactile detents for each setting. The manual bolt release and charging handle positions were standardized. Design memoranda discussed operation while wearing gloves. Winter trigger variants existed for extreme climate use. Stockwork departed from wooden forends and butt stocks. Synthetic and metal components formed the butt assembly. Cheekpiece height matched the planned optical sight axis. Butt plate shape distributed recoil against the shoulder pocket. Internal cavities accommodated return springs and guide rods. Assemblies were pinned to the rear of the receiver. The integrated optical sight distinguished EM2 from contemporaries. A fixed power unit sat inside a protective housing. The housing formed part of the rifle's carrying spine. Optics lifted the sightline above the barrel and hand. This reduced the need for traditional front and rear irons. The backup iron sights remained available on the receiver top. The optical sight embodied British marksmanship doctrine. Designers anticipated engagements beyond close urban ranges. Clear aiming points simplified training for conscripts and reservists. Range adjustment knobs allowed precise zeroing during armoury inspections. Armourers documented sight serials against individual weapons. Range logs recorded complaints about fogging or impact shifts. Manufacture required new jigs for the bullpup geometry. Existing Enfield fixtures suited conventional stocked rifles poorly. Toolrooms fabricated dedicated receiver and barrel alignment rigs. Gauges referenced the barrel extension rather than muzzle bands. Quality staff verified runout using dial indicators and mandrels. Tolerance stacks were recalculated to prevent cumulative misalignment. Production remained at pilot scale throughout development. Records list small batches built at Enfield. Some components came from external contractors, including BSA. Subcontract letters specified heat treatment and finish standards. Returned parts underwent acceptance inspection before binning. Rejected pieces accumulated in scrap crates near workstations. The .280 cartridge itself passed through several iterations. Neck dimensions, case length, and bullet profile were modified. Engineers sought better accuracy and improved penetration figures. Comparative firing at instrumented ranges generated large data tables. Trajectory records showed initial problems with dispersion and drop. Subsequent variants tightened groups and flattened mid-range trajectory. The definitive 7mm Mark IZ load emerged from this process. Ball ammunition used a jacketed bullet with specified weight. Velocity targets balanced recoil against retained energy at distance. Cartridge drawings fixed rim diameter to align with tooling. Factories like Radway Green adjusted presses for new case dimensions. Lot acceptance testing measured pressures and muzzle velocities systematically. EM2 prototypes fired this cartridge extensively during trials. British Rangers hosted comparisons with older .303 weapons. Sections fired deliberate, rapid and automatic drills under supervision. Observers logged stoppages, breakages and shooter comments. Inspection teams stripped rifles after set-round counts. Wear patterns on locking flaps received particular attention. Results showed controllable bursts and acceptable reliability. Automatic fire proved manageable relative to full-power rifles. Recoil impulses aligned directly into the shooter's shoulder. The straight-line stock and barrel configuration aided this. Optical sights increased first-round hit probability at test ranges. Reports from Malayan emergency deployments later echoed this assessment. Domestically, technical committees evaluated maintenance demands. Bullpup layout complicated access to some internal components. Armourers needed revised benches and holding fixtures. Stripping sequences differed from existing Lee Enfield procedures. Training pamphlets were drafted with new exploded diagrams. Workshops trialled the process on a small armoury sample. Spare parts provisioning raised further administrative points. Catalogue codes had to be assigned for every component. Bin labels, ledger entries, and requisition forms reflected codes. Optical units required separate storage and handling instructions. Seals, lenses, and adjustment mechanisms demanded careful packaging. Climate-controlled lockers were recommended for long-term site storage. While Britain refined its system, NATO emerged as framework. Alliance planners preferred common ammunition for simplification. Joint logistics studies emphasized shared calibers and components. American representatives promoted their T65 cartridge as standard. This round later formed the basis of 7.62 NATO. Comparative trials therefore acquired significant political weight. Aberdeen Proving Ground hosted major comparative tests in 1950. EM2 rifles and .280 ammunition travelled from Britain. Belgian FN lightweight rifles in .280 joined the programme. American T25 and related designs fired the T65 cartridge. US reports criticised .280 performance at longer ranges. Accuracy and penetration data shaped subsequent discussions strongly. British observers disputed the American test conditions. They argued that intermediate engagement distances were misrepresented. Memoranda stressed controllability over maximum theoretical range. US analysts prioritised penetration through armour and barriers. Their criteria aligned with existing .30 caliber expectations. Alignment on requirements never truly occurred during meetings. Back in London, minutes circulated between ministries. Files recorded frustration over differing American priorities. Defence economists, however, highlighted another constraint. Separate British ammunition implied separate industrial capacity. Alliance resupply would require dual logistics streams in wartime. And spreadsheet columns tracked costs for every proposed divergence. Canada introduced an additional political condition. Officials there preferred .280 but required American agreement. They would not adopt a caliber without US participation. This stance further reduced prospects for British independence. Combined diplomatic signals reached London in routine cables. Policy staff summarised them into briefing notes for ministers. Despite this backdrop, Britain briefly adopted the EM2. The rifle received the designation Rifle No. 9 Mark I. Adoption documents referenced the .280 cartridge explicitly. Announcements described it as the future standard service weapon. Tooling plans expanded from pilot to projected mass production. Training schedules were drafted around the new system. Production tooling changes started but never fully matured, costing officers calculated investments for full-scale conversion. Barrel-making lines required reaming tools for .280 dimensions. Receiver machining stations needed new cutters and fixtures. Optical sight assembly demanded clean environments and specialists. Procurement paperwork detailed quantities, delivery schedules, and penalties. Change of government altered priorities rapidly in Westminster. Winston Churchill returned to office and reviewed decisions. He placed NATO standardisation above independent small arms development. Briefings highlighted prospects for FN-FAL adoption in 7.62. Officials predicted American and Canadian interest in that pattern. EM2 therefore lost political backing despite prior adoption. The reversal occurred through standard administrative channels. Cabinet decisions translated into new War Office instructions. Letters cancelled planned mass manufacture of .280 rifles. Ammunition orders were reduced to experimental sustaining levels. Factories were instructed to maintain tooling but avoid expansion. Stockpiled components were boxed, labelled and warehoused quietly. Attempts were made to chamber EM2 for 7.62 NATO. Rechambered prototypes altered barrel and extractor geometry significantly. Higher pressure ammunition increased recoil and component stress. Reports noted harsh impulses during automatic firing sequences. Locking flaps and receivers experienced accelerated wear patterns. Weight increases eroded some original handling advantages. Engineers explored modifications to mitigate these problems. Gas system settings were changed to tame the cycle. Buffer assemblies were trialled in revised butt structures. Material substitutions for critical parts were considered and costed. None of these options matched the simplicity of adopting FAL. Administrative summaries concluded EM2 conversion lacked clear benefit. FN's rifle adapted more readily to 7.62 NATO. Its conventional layout simplified training transitions from previous weapons. International interest built momentum behind the FAL design. Licensing agreements allowed national variations without major redesign. For Britain, this became the L1A1 self-loading rifle. EM2 slipped back into limited trials and museum spaces. Within factories, EM2 jigs were reallocated or scrapped. Toolroom ledgers show fixtures reassigned to other programs. And inspection gauges were wrapped and placed in controlled storage. Barrel blanks intended for .280 were diverted or melted. Optic housings remained as shelf stocks without follow-on orders. Workers moved to FAL-related machining and assembly lines instead. The .280 cartridge followed a similar trajectory downward. Production shifted from development batches to minimal sustaining quantities. Radway Green Lines prioritized 7.62 NATO case production. Specialized forming dies for .280 saw reduced utilization. Some remained as reference tooling for test lots only. Range testing with .280 became an occasional experimental activity. Surviving EM2 rifles showed specific maintenance characteristics. Bullpup layout trapped fouling in the rear receiver section. Cleaning rods threaded from muzzle required careful guidance. And armourers used jointed rods and flexible pull-through devices. Gas systems demanded routine disassembly after extended firing. Carbon deposits accumulated around ports and piston heads. Optical units generated their own maintenance paperwork. Desiccant packs required periodic replacement in storage containers. Impact damage during handling had to be logged precisely. Units leaving alignment limits went to specialist repair workshops. Technicians used collimators and test targets for re-zeroing. Completed repairs carried signatures and dated acceptance stamps. Failure modes during trials were documented in structured tables. Entries listed round count at time of malfunction. Stoppage types were coded for statistical analysis. Feed issues, ejection failures, and light strikes were separated. The rifles exceeding malfunction thresholds triggered tear-down inspections. Findings informed dimensional tweaks and minor component redesigns. One recurrent issue involved trigger feel within the bullpup. Long linkages connected the forward trigger to sear. Friction and flex affected brake characteristics notably. Test shooters remarked on heavy, indistinct trigger releases. Efforts to improve this added complexity and manufacturing steps. No simple remedy matched conventional rifle trigger geometry. Transport logistics also favoured the eventual standard rifle. Packing crates for L1A One resembled earlier wooden transit chests. EM2's integrated optics demanded modified internal supports. Shock-absorbing inserts increased crate manufacturing time and cost. Export shipping assessments anticipated difficulty mixing crate types, and quartermasters preferred uniform packaging across battalions and brigades. Training establishments produced draft syllabi for EM2 instruction. Lesson plans covered safety states, loading and unloading drills. Automatic fire control with .280 formed a separate module. Optical sight zeroing exercises required additional range time. When policy changed, these documents became obsolete overnight. Revised syllabi substituted L1A1 nomenclature and 7.62 procedures. From an engineering perspective, EM2 matched its design brief. It delivered intermediate caliber automatic fire in compact form. Optics reflected forward-looking assumptions about infantry marksmanship. Mechanical systems functioned reliably within defined testing envelopes. Problems arose chiefly when forced into a full-power cartridge roll. Those constraints originated in alliance-level ammunition decisions, not drawings. The procurement narrative ended in ledgers, not firing pits. Budget lines migrated from EM2 development to FAL acquisition. Ammunition accounts followed, shifting from .280 to 7.62. Stock numbers for EM2 were frozen at pilot quantities. Disposal policies retained examples for reference and museum display. The remainder entered controlled storage or were broken for spares. Archive photographs show armourers handling EM2 on benches. Receivers rest on felt pads beside parts trays. Inspection lamps highlight machining marks and wear surfaces. Calipers, gauges, and screwdrivers lie arranged within reach. There is no visible ceremony in the images. Only routine technical work on a superseded pattern appears. Today, surviving EM2 rifles exist mainly in collections. Curators catalogue them under experimental or provisional service categories. Labels mention brief formal adoption followed by rapid reversal. Exhibit notes reference NATO standardisation and 7.62 NATO decisions. Visitors see an early bullpup with integrated optics and intermediate cartridge. Behind that artifact lies a sequence of spreadsheets and minutes. The EM2 story illustrates engineering shaped by alliance arithmetic. Its mechanism aligned with lessons drawn from wartime engagements. Its cartridge parameter choices came from structured analytical panels. Its rejection resulted from shared logistics, not isolated technical failure. Rifles in this case followed numbers on standardisation charts. The EM2 remained accurate on ranges while paperwork moved past.